All right, so we're talking about the special homework for 4-5, 4-7, and 4-8. And in particular, we're looking at number 3, which is a proof by cases, right?
Yep.
And when we write the statement as an if-then, it could be something like this. If x is an integer, then the product x times x plus 1 times x plus 2 is divisible by 3. Now, I tried to kind of help by giving you a very similar problem in class notes where it was that the product of two consecutive integers was divisible by 2, of course. So when we write this proof, we sure do look at the fact we're trying to show something is divisible by 3 to know that D is 3, but we just assume X is in Z. And of course, we wish to show that 3 divides this product of X times the next two consecutive integers, whatever you call it. I wouldn't call this whole thing X. I would, like I said, call it N or something. But the point is, we want to show something has to do with dividing by 3. So using the QR theorem with D equal 3, you did that right. And you did set up the cases. What are the 3 cases? Applied to the hypothesis object, applied to the X.
X equals D times Q.
Well, what is it?
3,
3 times
3Q.
D. Or,
X equals 3Q plus 1,
good.
or X equals 3Q plus 2.
Exactly. And this is all where Q is some integer. And that sets up our 3 cases. In each case, we want to show the same result, and that is that this expression, x times x plus 1 times x plus 2, has a factor of 3 in it. Do you agree?
Yes.
Right. So, uh, we even started this in class, didn't we? Or did we do a similar one? Maybe we looked at x squared equals either 3k or x squared equals 3k plus 1. I guess we looked at that. But the point is, we have these 3 cases. In each case, it's the same wish. We're trying to show something about this expression, x times x plus 1 and times x plus 2, namely that 3 divides that whole expression. So again, misunderstanding what you were trying to do, it's almost as if you thought that, in different cases you wanted to get a, a remainder of 2. And maybe you were confusing this, with a different problem or something. I'm not sure. But the point is, the wish is always going to be the same in every case, whether it's a compound wish or, in this case, a simple atomic wish. We just want to pull a factor of 3 out of this, right? And let me just show you a couple of hints. For the first case, what should we suppose? What would be our hypothesis?
Suppose X equals 3Q.
Yep, for Q's and Z. And it's the
3Q.
same wish, right? We wish to show that x times x plus 1 times x plus 2 turns out to look like 3 times some integer, we'll just call it m, that it's a multiple of 3.
Ah.
So we just look at x times x plus 1 times x plus 2, and we just substitute in 3q everywhere, of course, that we see in x. And one of the hints I tried to give when we looked at the similar problem about 2 consecutive integers is you don't really need to do any multiplying. We see a factor of 3 right here. right? It's 3 times q times this binomial factor times this binomial factor. So if you just pull the 3 out, then the q times the 3q plus 1 times the 3q plus 2 multiplied together. We don't even, like I said, you don't have to do the work of multiplying that all out. That'll turn out to be our m. And then we just talk about, since q is in z, right? And z is closed, what are the operations that are being used to build that m?
Multiplication and addition.
Yep,
So
so it's closed under multiplication and addition. You can even, abbreviate that. M equals Q times 3. Oops, I'm missing my 1 here, aren't I? Let me just put my 1 in there. Oops. Come on, little whiteout tape. Do your magic. 3Q times what? 3Q plus 1 times 3Q plus 2. That whole thing is still just, a product and sum of integers. That is an integer. So in fact, x times x plus 1 times x plus 2 does look like 3 times m, where m is in z. And that means 3 divides that, right?
I see.
Now in case 2, it turns out, that we suppose x equals 3q plus 1. But again, we don't have to do a whole lot of multiplying out. We can save ourselves the headache of multiplying all that out. It's the same wish. We wish to show that this product of these 3 consecutive integers, starting with the x, that is our hypothesis object, is equal to 3 times m. Oops, square bracket. So x times x plus 1 times x plus 2. Now we do have to use parentheses, and you do a really nice job, I noticed, of using parentheses. But it turns out that this third expression is 3q plus 3, isn't it?
Mm.
And we can just pull a 3 out of this, and it'll leave behind, a different binomial factor. But the point is, we can just get a 3. Yeah, I mean, if you multiplied it out, and, you can do that. It's not wrong to multiply it out. It's just a lot of work. But you can pull a 3 out of that and be left with 3q plus 1 times 3q plus 2. And what would that third factor look like after we factor out the 3 from both terms?
3q q plus 1.
Yep. And see, and this is now our m. And in the third case, when x equals 3q plus 2, when we put in 3q plus 2 for this middle x, this factor becomes 3q plus 3, and you'll be able to factor out a 3 from it. I think this becomes 3q plus 4, which doesn't matter. It's fine. It's still sum and product of integers. And this is 3q plus 2 in the third case, you see. And again, talk about why m is an integer. And then you do case 3. So we always want, so, your multiplication was okay, but then you just didn't factor the 3 out of that constant term, which indicated to me that you didn't really seem to understand what we were trying to do, which is to show that this product always looks like a multiple of 3, no matter which expression we're using, no matter which case we're in. Does that make sense?
Yes, I see.
Now, if you want to resubmit that, you can go ahead and resubmit that.
I appreciate that. I will.
Okay, I'm glad that you understand. I've been, busy grading, everybody's submissions and haven't completely finished grading those, but I can sure look at some of your other submissions here. I can just take a glance at those at least. Hi Darius, how are you? I'll do that while Darius lines up a question here.
I'm doing great. How are you?
Great. What can I do for you? Do you have some questions?
Well, to be honest, I'm still clueless about this whole thing. So,
I'm sorry, what? Did you say you're stumped about the whole thing?
yep.
Oh my goodness. So have you been able to work through the problems from the first special homework? Or are you still even working on some of those?
I did, but I did along with I think I did in the tutoring session, but I still don't understand it as well.
Yeah, that's kind of the problem with it's kind of hard, to try to learn a whole lot of material in just a few days. Is there a specific problem from special homework 4.1 to 4.4 that you would like to look at? I'm looking,
Yes, some nipple feel, but to be honest, I don't really think I'm gonna do well on that test.
I'm sorry to hear that, but we can go over some of those problems if you, are you able to write the the given statements as if-then statements? I mean, are you able to do that? I mean, like that's kind of the first step. Do you know even what you're supposed to assume and what you wish for the different statements? Shall we just at least kind of try to get that much sorted out?
Nah,
Okay.
yeah, the thing is, I even contacted my advisor last time trying to draft this code, but they told me that I can't draft it. If I do, I will have to draft every other course that I'm taking this semester.
So uh,
So
why don't we just get what we can, you know, out of this session? Do you know the difference between proving an existence statement and proving a universal statement?
no.
All right. Well, that's a real kind of fundamental thing. By the way, Nora, your problem 8 looks fine. I was able to just read that right now.
Oh,
So,
I had no idea it was correct.
but let's talk about, proving existential statements versus universal statements, because that's a really important thing to understand. Let's make a little chart, okay?
Okay.
All right. Now, so let's say we want to prove an existential statement. Do you know the kind of basic um, form of an existential statement? Like there exists an X
Yes.
in some domain D such that there's some property that X has, right?
Yes.
As opposed to a universal statement, right? If we call, here's existential versus universal. So this would be something like to prove a for all statement. There might be several objects. It might not just be one, but it might be several different objects. But the point is, usually we always try to write a universal statement as an if-then, and there's a reason for that. And the reason for that is because we have 3 different proof methods, and they all hinge on understanding how to write universal statements as if-then statements, and understanding every universal statement can be expressed as an if-then type statement. All right, but let's do the easy one first. The easier kind of statement is an exist statement. So this is what we have to do. We do some scrap work. And find a specific X that works. Whereas to prove a universal statement, we cannot prove using an example. It's a big difference. You can prove an existential statement by finding an example that works. And there are 2 steps in that process. One is to verify that our choice of X is in the domain D, whatever that domain D is. We have to make sure that our X really lives in that domain. So maybe the statement is about prime numbers, and then we have to verify that our choice of X is a prime. Or maybe it's a statement about even numbers and odd numbers. We verify that our choice of A and B are, perhaps even and odd. And then the second thing that we do is we verify that the property P of X, or this predicate P of X, is true for our choice of X. Whatever we have, found in our scrap work, we verify that P of X is true for our choice of X. And if we do those 2 things, we've proven an existential statement. To prove a universal statement, we have 3 possible methods. These are harder proofs. We must use variables. We can't use examples. We have to use X's and Y's and A's and B's. And so the direct proof method, we assume that X is in D and that P of X is is true. Just assume the hypothesis. And then we wish to show that the conclusion follows, whatever that is. That's for the direct proof. But there are 2 other proof methods. There's contrapositive. So we assume that we have an object X in D, and we also assume that Q of X, the conclusion is false, and what we wish to show is that not P of X is true. Because remember, the contrapositive of if P then Q is if not Q then not P. So we just milk that fact. Oops, we can't see that very well with this light. Let me write that. If not Q, then not P. It's just a direct proof of the contrapositive. We assume not Q because that's the hypothesis for the contrapositive. and we try to prove not P follows. And then there's proof by contradiction, which is assume the negation is true, and then show that leads to a contradiction. So for the other proof method, for universal proof, is proof by contradiction. And we just assume the negation of what we wish to prove is true for this method. So we assume there exists an X in D such that P of X happened and Q of X failed. Because we're trying to prove if P of X happens, then Q of X follows. And that's a for all statement. So we just assume the negation. And the negation is that there exists an X in that same domain such that, P and not Q happens. And it's always the same wish. We always wish to show this leads to a contradiction. So let's look at some examples of different kinds of statements. And let's just kind of think through what we have to do to prove them. All right, so for existential statements, we've had numerous examples of existential statements that we've needed to prove, and we just cook up examples. So here's one. There exist integers. In fact, I think it was there exist odd. Was it odd or even? There exist, well, I'll just make one up. It doesn't matter because it's true for both. There exist odd integers, A and B, such that A plus B over 2 is even. Okay, you can find odd integers A and B such that this turns out to be even. Okay. Another one would be something like there exist primes P and Q such that say 2 to the Q plus P is composite. And of course you have to know the definitions to know, when you've got yourself a prime number and when you've got yourself a composite number. We can think of maybe, here's one more. There exists a rational number X and an irrational number Y such that X times Y is actually rational. You can find an X that's rational and a Y that's irrational, so the product is rational. So we can come back to these, all right? But these are just examples of existential statements. Let's look at some examples of universal statements that you might be asked to prove. For all integers n squared plus 3n minus 5 is odd, we would use proof by cases with d equals 2 for that one. But you wouldn't use examples to prove it. You couldn't plug in a particular integer in to prove that, but you can prove that this expression always looks odd. Or there's another kind of basic kind of universal statement. If x and y are rational, I'll write this one as an then x squared plus y is also in Q. Okay, so R rational, that means x and y are in Q. Implies x squared plus y is in Q. That's an if-then statement that you can prove without using examples. You can prove it in general. It's always true. If n is an integer and n is greater than, let's say, 4, then n squared minus 4 is composite. You can prove that's always true. And we can go through some of these. If A divides B and B divides C, then A cubed divides BC squared. You could prove that. If X is rational and Y is irrational, then 2x minus 3y is irrational. We would have to use maybe proof by contradiction for that. These others can all be proven directly, but there's some other things we've proven using indirect methods of proof. For all integers x, if x cubed is even, actually I'll make it even easier. If x cubed is odd, then x is odd. We would use either proof by contradiction or proof by contrapositive for that. And we can do one more with divides. For all A, B, and C, and Z, if A squared does not divide B squared plus C squared, then A does not divide B, or A does not divide C. Because this involves does not divide, we know that would be hard to prove directly, so we might try proving it indirectly, like using proof by contrapositive. So we can go through some of these and try to write the proofs. There are other things, that you need to be able to do, of course. You need to be able to, for the test, if you have two numbers, can you find the Q and R guaranteed? The quotient remainder guaranteed by the QR theorem? for dividend A, and divisor B. So if I give you an A and a B, and I ask you to divide A by B, can you find the Q and R that are guaranteed? So this would be, an example. So like part one, A could be, I don't know, 33, and B could be 4, but we could play it, in the negative way. A is negative 33 and B is 4. We could play a few of those games. Do you feel comfortable with these? A is 8 and B is 10. Or A is, I don't know, 35 and B is 7. We could play those games. Do you know how to do these? Finding the Q and the R. Remember, A equals BQ plus R, where 0 is less than or equal to R is less than D. Why don't we warm up with some of these? Let's see if we can get some of these done first, and then we can go back to the proofs.
I don't know. I think I came across something like this when I was reviewing the textbook today.
Yeah. Yeah, because this is, we did this in class. We had a big example with lots of parts, and we practiced doing this. But why don't we do it now? If A is 33, so that's our dividend, we're going to divide 33 by, um,
4.
yeah, but maybe I should call this D instead of B. We usually call it D, don't we? Let me change this to D. It makes more sense to call it the divisor D. Yeah, so if we're dividing 33 by the divisor D equals 4, what quotient do we get? And what remainder do we get? Let's look at that. All right, so 33 equals 4 times a quotient plus the remainder. And the remainder can't be too big, right?
Yes.
What are the possible remainders when we're dividing by 4?
Like 2.
2 is one of the possible remainders. How many possible remainders are there if we're dividing by D equals 4? You know how many possible remainders there actually are?
Oh, if I defer that, we can get 1.
1 is possible, 2 is possible. What about 0?
Maybe 0.
Sure, 0 is always a possible remainder because R, the remainder, can always equal 0. But it could be bigger than 0 as long as it's less than our divisor, 4, right? We're good to go. So what's the biggest remainder that we might get if we're dividing an integer by 4?
The biggest might be 3.
Yeah. All right, good. So how many, well, how many times does 4 fit into 33? Or what is the quotient when we divide 33 by 4 is a better way to ask that question, actually.
That can be maybe like 8.25.
Okay, so it fits in. So you take 8, that gets us to 32, right? 4 times 8 is
Yes.
32. So what's the remainder when we divide 33 by 4?
1.
Yeah, good. Now if we're trying to divide negative 33 by 4, this is kind of an interesting game. I'll draw a picture up here. It means that when we draw the number line, we start at 0 and we're counting backwards, negative 4, negative 8, negative 12, keep on going. And
Okay, so I got a little confused on this negative part.
all right, well, the point is we want our grand total to be negative 33, right? So we're, if we multiply 4 times -1, it gets us back to -4, right?
Yes.
But if we multiply 4 times -2, we're jumping back to -8. If we multiply 4 times -3, where does that get us?
I'll be negative 12.
So we just keep doing this, right? -16, -20, -24, -20 what? What happens next? How do we multiply by -6, we get to -24. What about -7? What's 4 times -7?
28.
-28. Let's keep going. What's the next one?
-32.
That would be if we multiplied 4 times -8. Good. Keep going because we're not at -33 yet. See, -33 is right here.
So the next one will be -36.
So we overshoot. We go all the way back to -36 by multiplying 4 times -9. Do you know why we do that?
That's the part I got confused on. No.
Well, because our remainder can't be negative. If we stopped at -32, then to get to -33, we would have to subtract 1, but we can't have a negative remainder. So when we're trying to hit -33, we have to overshoot the -33 and go all the way down to -36. Because then if we're at -36, we can come back with a positive remainder that's legal. What would, right? 4 times -9 gets us to -36. What can we add to -36 that would get us back to -33?
So if we do that -33 to so the remainder will be 3.
Yeah, and that's legal. It's perfectly legal to have a remainder of 3 because it's not negative. We can't have a negative remainder, right? And it's not,
So
it's
uh,
less than 4. See what I mean? That's what's
yeah.
going
So
on with
can I
that.
ask a question?
Sure.
So based on based on this, the remainder cannot be higher than the divisor, right?
And it can't even, that's right, it certainly can't be larger than the divisor, but it can't even be as large as the divisor. Like if we're dividing by 4, we don't want to get a remainder of 4. If we get a remainder of 4, that means we could have had a bigger quotient in absolute value anyway. Yeah, you don't want your remainder to be 4 or 5 or 6 if you're dividing by 4. You want your remainder to be 0, 1, 2, or 3.
Okay.
All right, let's try the next one. What if A is 8? We're trying to hit 8, but we're dividing by 10. Now here the divisor is larger than the dividend. Is there anything that we can multiply by 10 and then add a remainder that's between 0 and 10, and get 8?
Uh,
This is special because the divisor is larger than the dividend. D is larger than A. This is special. What if we multiply 10 by 0? What would the remainder then be?
0.
Well, let's see. Let's see if that balances. If we put 0 here, on the left we have 8. On the right, what do we have? 10 times 0 plus 0. Is that 8?
No.
No. But what if we put an 8 here? Doesn't that equation balance?
Yes.
And is 8 a legal remainder when we're dividing by D equals 10?
No.
Why not?
Because, oh, yeah, yes, yes. The divisor is 10.
Right.
Yeah.
So when the dividend is less than the divisor, the remainder will equal the dividend and the quotient will be 0. If the divisor is larger than the dividend, it doesn't fit into there at all. So you put 0 here, and the remainder is going to be
The 8.
yeah, it's going to equal the dividend. And of course, if A is 35 and we're dividing by 7, what's the quotient?
So it'll be, so wouldn't it be like 7? I mean, 4?
Let's see, 4 times 7 is 28. We need a little bit bigger quotient than 4.
Uh, so maybe 6?
6 times 7 is 42. That's a little too big.
Okay, then I guess it'll be the 5.
Good. What is 7 times 5?
It's 35.
Right.
Oh,
And that's when the remainder is 0. 7
mhm.
actually divides 35. It hits it right on the nose. So the remainder is 0. All right, now let's think about some of the other kinds of problems we might have to do with the divisor and the quotient. We have 2 definitions. A div D and A mod D. This is all with the setup that A is equal to DQ plus R, where 0 is less than or equal to R is less than D. I mean, it's still that setup. So A div D is the quotient, and A mod D is the remainder. So one of the kinds of examples that we've seen is something that plays with A mod D. If A mod, let's say D is 4 again. If A mod 4 is equal to 3, what is A squared mod 4, for example? That's one of the kinds of problems that we've seen. Well, let's just think about the fact that we lean in on. There's a fact that we use when it comes to translating the mod function to an equation. A mod D equals R means that A equals DQ plus R. 0 less than or equal to R is less than D. Okay, so if we're given that A mod D is a particular value R, we can understand that to mean that the remainder when we divide A by D is this mod value R. So we can use that here. Let's just play the game. All right, we have that A mod 4 equals 3. What do we wish? We wish to find A squared mod 4. So we have to translate the fact that A mod 4 is 3 into an equation. All right, so we'll use the fact. The fact says that if A mod D is R, well, what's D here? It's 4, and R is 3. Then we can write A is equal to that divisor times some quotient Q plus 3. That quotient is an integer. So we can translate this information into this equation about A. That's what it means to say that A mod 4 is 3. When we divide A by 4, it says we're getting a remainder of 3. We don't even know what the quotient is. It's just an integer. And we want to talk about A squared. So let's look at it. A squared would just be this expression squared, because A is equal to 4Q plus 3. Then A squared will be 4Q plus 3 squared. And that's 16Q squared plus 24Q plus 9. But we're trying to figure out what A squared is mod 4. That means we need to figure out what the remainder is when we factor out a 4 from all this. Well,
So, quick question.
yeah.
I understand how we got like the 16 and the 9, but I don't understand like the 24.
Well, you can go over to the side and just multiply this out using our FOIL method. 4Q times 4Q is 4Q quantity squared, plus 4Q times 3 is 12Q, plus 3 times 4Q is another 12Q, plus 3 times 3 is plus 9. And when we combine the middle terms, 12Q plus 12Q is a grand total of 24Q. And so here we're trying to divide out a 4. We can pull a 4 out of the 16 and we can pull a 4 out of the 24. We can also divide 9 by 4 using the QR theorem, can't we? That's just like we played the game here, with different dividends and the divisor 4. Well, let's let 9 be our dividend. Let's divide 9 by 4. If we factor a 4 out of 9, what's our quotient? And what's our remainder? We're just going to play the QR game with 9.
1?
1. 4 times 1 is 5.
2.
Yeah.
What I was saying is if we do like 4 times 2, we get like 8 and then 1 is remaining. That's why.
You're right. Okay. Yeah. Then yeah. Okay. I see what you're saying. You're saying the remainder is 1. Great. And then that's actually what A squared mod 4 is, because we can take the 4 out from all of these, right? Leaving, behind integer terms here. And we have plus 1. This is A squared mod 4. It's the remainder that we get when we divide A squared by 4. This is like the big Q, this is like the big quotient. You can call this thing, Q hat. So since A squared equals 4 times Q hat plus 1, A squared mod 4 is 1. That's our answer. So these are games that we played with mod. Do you know all your definitions? We have a slew of them.
There are the definitions like n equals 2k, where k is some integer within z.
Yeah.
Is it something like, yeah.
Yeah. All right, good. Well, then let's practice. Let's start proving some of these statements. Let's prove, proving our example statements. Let's start with number 1, because existent statements are the easiest. Let's just work on those first. All right, number 1. It says there exist odd integers, we'll call them A and B, such that A plus B over 2 is even. So let's look at our steps for proving existential statements. To prove an existential statement, whether we have one object or in this case 2 objects, we do some scrap work. We're going to try to find a specific X that works. Here we're actually going to find a specific A and B that works, right? This is of the form, there exist A and B in 2Z plus 1, such that A plus B over 2 is in 2Z. This is our predicate. And this is our there exists. Okay, so it's of this form. It's just that we have 2 objects, A and B. And this is the property, P of A, B. All right. So let's do some scrap work and let's see if we can find some odd integers, A and B, such that their average is even. All right. So we need to find an A and a B, and then we want to look at A plus B over 2. These both have to be odd. And we need this to be even, right? And then we'll just verify. So what would be an A that would work and a B that are odd? Just give me 2 examples.
2 and 3.
Well, let's look at what has to be true. We need odd integers, A and B. Is 2 odd?
Oh, okay. Then 3 and 5.
Well, let's try 3 and 5. Okay, great. They're definitely both odd, right? We're going to be able to prove that these are odd. We're going to verify that because the first thing we'll do if we figured out objects that work is we're going to verify that our choice of objects are in the domain. Here the domain is the domain of odds. But we're also going to have to verify that the property holds. So here's our property that we want to hold. All right, what is 3 plus 5 over 2?
Three plus 5 is 8. We got 4?
Yep, is 4 even?
Yes.
Great. So now we're ready to write our proof. We have found 2 odd numbers whose average, A plus B over 2, is even. So we can just write it up. We can consider A equals 3 and B equals 5. Now we have to verify that these are odd. How do we verify that 3 is odd? How do we have to write it to show that it's odd? We need to know the definition of odd.
Like n equals 2k plus 1.
Okay, so what's our K?
So our k here will be the 3.
3 equals 2 times what plus 1?
Isn't it k 4?
What's 2 times 4, Darius?
6. Oh, 8. My bad.
Well, is 8 plus 1 equal to 3?
No. So that'll be 0.
Okay, if we put a 0 in for K, what is 2 times 0 plus 1?
That's 1.
Okay, so we need a little bigger than 0. And 5 is equal to 2 times some integer K plus 1. You find the K later, okay?
Yeah.
So, but the point is we just have to say it. We have to just show why 3 looks like 2K plus 1 and why 5 looks like, say, 2k hat plus 1. It's a different k. And we just say, so 3 and 5 are odd. All right, so we just verified that our objects come from the correct domain. We just did step 1. We verified that our choice of objects, here it was A and B, maybe it would just be one object, is in the domain that they need to come from. Here the domain is just the domain of odds. The next thing to do is verify that the property holds. Well, the property is that their average was even. Well, we did that. We just, we just write it. So just say it. Also, A plus B over 2 is 3 plus 5 over 2, which is 4. And how would we show that 4 is even? We got to verify that it's even. We have to show that it's equal to a multiple of 2. What would we put here?
To make it even,
Yeah. I mean, it is even. We're showing that it's even. Yeah. 4 equals 2 times what?
1.
Right. All right. I think it's 2, but that's a challenge, Jarius.
Oh, we are trying to make it even to that 4.
Just trying to factor out a 2 is all I'm trying to do, man.
So 2 getting a 2 everywhere.
Yeah. Okay, so it's because of our choice of 3 and 5. We could have used, we could have used 3 and 7, and we would have gotten something different here, but that's okay. Let's look at the next statement. It says there exist prime numbers, and we're not even told that they have to be different. P and Q, such that it's another existence statement. It's our job to cook up the P and Q that makes 2 raised to the Q plus P so that that expression is composite. So let's do some scrap work for this one, and let's see if we can find a P and a Q. They have to be primes. And then we have to look at 2 raised to the Q plus P, and that needs to be composite. All right, so let's try some. Let's try to find some P's and Q's and see if we can find some primes that'll work. What are your favorite prime numbers? If you're asked to look for prime numbers, what do you usually start looking at?
A 1.
But a prime number can't be 1 because the definition of prime only applies to integers that are 2 or larger. Do you know can you write the definition of a prime number down?
Yes, I think I wrote it down. N can only be divided by 1 in itself.
That's part of the definition, but there's a tiny bit more, and that's that n must be greater than or equal to 2. Okay, great. So what's the smallest prime? Now this is something you should know.
So 3,
There's one that's even smaller than 3. But
2,
3, yep, 2 and 3 are both primes, but 3 is certainly prime. So maybe we can try P equals 3. What would you like to try for Q?
7.
All right, let's try. Those are definitely prime. Now we got to look at 2 to the Q plus P. So it's 3 to the 7 plus, no, 2 to the 7, my bad, plus 3, right? Is that right? If Q is 7 and P is 3, all right. So 2 to the 7, well, I know that 2 to the 8th is 256. So 2 to the 7 is 128. So this is 128 plus 3, and that's 131. Is that composite? Can we factor that into non-trivial factors? I think not. Let's try different ones. Let's try some smaller ones. That's not composite. This is prime, I believe. Its only factors are 1 and 131, I believe. 7, see, the only thing that might fit into it would be 7, but nope. Does 7 fit into 15? No, nope. Okay, let's try different ones. I like using small ones. P equals 3 is nice and small. Can you give me a Q that's smaller than 7? Is there a prime we could try that's smaller?
So is 5 not gonna work in the fit in
Well, we
there?
can try. Let's try it. So it's 2 to the Q, so that'll be 2 to the 5th, plus our P is 3. What's 2 to the 5th?
125?
No, that's 5 cubed.
Oh,
2 to the 5th. You should know your powers of 2. Okay, let's just practice powers of 2. 2 to the 0 is 1. 2 to the 1 is 2. What's 2 squared? Let's look at our
4.
powers. Yeah. 2 to the 0 is 1. Then 2 to the 1 is 2. Good. 2 squared is 4. Keep going. What's 2 cubed? Just keep multiplying by 2. 4 times 2 is 8. 2 to the 4th, what is that?
12. Oh, no, not 12. My bad.
I think we got some basic algebra issues going on here. 2 to the 4th is 16. 2 to the 5th is 32, okay? Anyway, this is 32 plus 3. What is that?
35.
And is that composite? Can we factor that in a non-trivial way? Sure. It's 5 times 7. So these will work. This will work. This is definitely composite. So we can write it up. We found our example by just trying some different values. These existence proofs shouldn't be too bad. They should be fairly straightforward. Let's try to write it up. We'll verify that our choice for our variables, our values really are prime. And we'll verify that this expression is composite. That's our predicate. That's our property we want to verify. So we're just going to go ahead and consider P equals 3. Good job finding 2 primes that work. I mean, we don't know necessarily that they're going to work till we try it out, but they did. So consider P equals 3 and Q equals 5. And then we write it up. What would we have to say about 3 and 5 to push this proof through? What domain do they have to come from? What kind of numbers do they have to be?
Can you repeat the question again? Yeah, can you please repeat the question?
Can you see the video? It's right at the top.
Oh, you were muted, that's why.
Well, I mean, I was waiting for you to just look. Question's right here. Can you see it? Do you have video, Darius?
Yes, I do.
Why don't you read the statement?
There exist prime numbers P and Q such that 2Q plus P is composite?
So 2 to the Q plus P has to be composite. And P and Q need to be prime. So we need to verify. How do we verify that 3 is prime? How do we verify that 5 is prime? Since only 1 and 3 divide 3, and only 1 and 5 divide 5, what can we say about 3 and 5? Well, they're both greater than or equal to 2. We see these are prime. We found two numbers that are bigger than or equal to 2 that only have 1 and themselves as their divisors. That's how we verify prime. And now we have to verify that 2 raised to the Q plus P is composite. Well, that's 2. Our P is 3. Q, 2 to the 5 plus 3. And that's 32 plus 3 is 35. We have to verify that that is composite. So we have to know the definition of composite. We know we have to factor it into two factors, A times B. And we just have to verify that these factors are integer factors greater than 1. Well, notice 3 is greater than 1, and 5 is greater than 1, or you could say 1 is less than 3, and 1 is less than 5. It doesn't matter how you say it, but the point is these are non-trivial factors, and 35 equals 3 times 5. So 35 is composite. So you have to know the parts of the definition of prime and the parts of the definition of composite to prove a simple existence statement about primes and composite numbers. You see? Any questions?
No.
All right, let's look at number 3. Number 3 is our last existence statement that we're practicing on tonight. It says, there exists a rational number x and an irrational number y such that, so we'll get this property that their product is rational. Now, this is true, but we have to hunt for the correct rational number x that will make it work. There's only one rational number that's going to make this true. X has to be rational, and y cannot be rational. And we want xy to be rational. So we need to pick an x that's rational, and we need to pick a y that's irrational, and then we need xy to be rational. Nura, can you think of a rational number that we'll be able to multiply by an irrational number and get a rational product?
I'm following along. I have x equals 0 over 1.
Yep, that's definitely rational. And what would you like to use for your irrational number?
I have square root of 2.
Yep, square root of 2 is our classic example of an irrational number. But then xy will be 0 times square root of 2, and that's 0, and that's rational. So x equals 0 is the only rational number that does this job. And you don't even really have to pick an irrational number. You can just say y is irrational, because no matter what irrational you pick, x times y will be 0 times y. It'll always equal 0. So in our proof, you can either pick y equals square root of 2, or you can just say y is any irrational. We can let x equal 0 and y be irrational, or we can say y equals square root of 2. If we want a particular irrational, we can do it either way. Then x equals 0 over 1, and 0 and 1 are integers. And of course, 1 is not equal to 0. So x is rational. We assume y is irrational, whether it's, or assume y equals square root of 2. Either way you do it, xy is 0 times y, or you can say 0 times square root of 2. That's fine. But any way you slice it, it's 0, which we already proved is rational. Or verified, I think is easier to say. We already verified is rational. So for this simple existence proof, you can pick any irrational number or just say y is irrational, but you have to pick x equals 0 or it won't work. Let's practice some of these universal statements. Do you have any questions on that, Darius?
No.
Existence proofs are supposed to be fairly easy. We just have to come up with examples that work. What does it mean that they work? It means that the objects we pick are from the correct domain, and then the property, whatever it is, actually holds. Just like here, we picked primes 3 and 5, we verified their prime, and then we verified the property that 2 to the q plus p is actually composite. In our first example, we picked odd numbers and we verified that they were odd. And then we looked at a plus b over 2 and we verified, I should say, which is even. We verified that their average is even because 2 is an integer. There's always two things we have to do when we're proving existence proofs. Pick objects that are in the correct domain, verify they live in that domain, and then verify the property. But it's a very different kind of story when we're trying to prove examples of universal statements. These are our universal proofs. Let's look at some of those. Number 4 was this one. For all integers n, the expression n squared plus 3n minus 5 is odd. Now this is one of these that we're going to have to do by cases because we're trying to prove something is odd and there aren't any 2's around. There's no way to make this look like 2k plus 1 unless we introduce the 2's. So this is going to be a proof by cases. Might want to write this as an if-then. If n is an integer, then n squared plus 3n minus 5 is odd. So we're going to assume that n is an integer, and then what we wish to do is prove that that expression turns out to be an odd number. So assume n is an integer, And what we wish to show is that n squared plus 3n minus 5 is odd. So we're going to use the QR theorem so that we can get some 2's in here, so that we can show that this is odd. The definition of odd means we need to see some 2's, and we don't see any. So using the QR theorem with d equals 2, we have information about this integer n. We know we can divide it by 2, and it's either going to look like 2 times q, or it's going to look like 2 times q plus 1. Because when we divide n by 2, there are 2 possible remainders. What is the remainder that we got in this first case 1? In other words, if n winds up looking like 2 times q, what's the actual remainder there? D is 2.
So that'll be 0.
That's exactly right. So that's one possible remainder when we're dividing an integer by 2. But the other possible remainder is here. What's the remainder in this case 2?
That's 1.
Exactly. So, but in both cases, we want to show that when we divide this expression by 2, we get a particular remainder. What remainder are we shooting for when we're trying to show something is odd?
A remainder that is not even.
Yeah, so the remainder can't be 0. The remainder has to be the other remainder.
It's got to be 1.
That's right.
1 or maybe, no, 1.
Yeah, yeah, because there are only 2 possible remainders. We want to get the 1. So let's suppose n equals 2q, where q is in z. It's still the same wish. It's the same wish in every case. We wish to show that n squared plus 3n minus 5 looks like 2 times some integer, say m, plus 1, right? That's what it would mean to say that that's odd. Do you agree?
Yes.
All right, well, let's do it. Let's take a look at that expression, n squared plus 3n minus 5, in the case when n equals 2q. Okay? So what do we get when we plug in 2q for n in this expression? 2q quantity squared, that's our n getting squared, plus 3.
So we have, okay.
Keep going. You tell me what to write.
So wouldn't that be 4?
We can go over here, 2q times 2q. Right? So the 2 times the 2 is the 4. What is q times q?
2 times 2 is 4.
Yep, 2 times 2 is 4. But now we have to multiply the q times the other q. How do we write that usually? That's q squared. That's what q squared means. It's 2 copies of q multiplied together. So this is 4q squared. But then we have 3 times n. So it's 3 times 2q. And then we have minus 5, right? So what's 3 times 2q?
6q.
Yeah. And now we want a plus 1 hanging off the end, right? So we divide negative 5 by 2. It's 2 times something plus 1. What is the quotient that goes right here? We're going to put that in right here. It's going to be 2 times something plus 1. What goes here?
2 times 0.
Well, what is 2 times 0, Darius?
Okay.
So 2 times 0 would be 0, right?
Yes.
And 0 plus 1 is a grand total of 1 on the right side. That's not equal to negative 5. We have to overshoot the negative 5. This is another situation where Here's -5, right?
So we go beyond the negative number.
Exactly. -2, -4. We go beyond it to what?
6.
Yeah, -6, so that we can come back with that remainder of 1. So how many copies of -2 did we jump by?
3.
Yeah, so it's a -3 here, right? Because we're going backwards. So it's 2 times -3 plus 1. And now we can pull a 2 out of those 3 terms, leaving 2q squared plus 3q minus 3, whole thing plus 1. And now we get, and that's odd. We just need to talk about why this is, I guess I called it m here. Okay, I can put an m here. But we have to talk about why that's an integer, right? Well, it is an integer because we know q is an integer. Since q is an integer, and what are the operations being used to build this m right here? Well, we're using multiplication because q times q is q squared, and 2 times q squared is multiplication. We're using multiplication to build the 3q, right? We're multiplying 3 times q. So we're definitely using multiplication, and we're using addition because there's a plus here, but we're also using subtraction. So we're using all 3 operations. So we talk about the set Z being closed under those operations. So, and it's because Q is in Z. You can also say 2 and 3 are in Z, but we don't have to. We know they are because they're not letters. They're just numbers that are integers. But since Q is in Z and Z is closed under, let's see, multiplication, addition, and subtraction, this expression m equals 2q squared plus 3q minus 3 is an integer. So did we get our wish? Did we show n squared plus 3n minus 5 equals 2 times an integer plus 1?
Yes.
Good. So n squared plus 3n minus 5 does equal 2m plus 1, where m is in Z, which means it is odd by definition of odd, right? So that's the first case. That was the case when n looked like an even number. It doesn't matter whether n is even or odd. We should be able to get that this expression, n squared plus 3n minus 5, turns out to look odd. All right, so case 2, what would we suppose for case 2, Darius? What would we assume or suppose? We just finished case 1. So this is our case.
Case 2 is n equals 2q plus 1.
Good. Great. It's the same wish. We still wish to show that n squared plus 3n minus 5 looks like 2 times an integer plus 1. That's the same wish in every case. Okay? So now we just do the same thing, but instead of plugging in 2q, we're going to plug in 2q plus 1. So let's do that. N squared plus 3n minus 5 is 2q plus 1, 1e squared, plus 3 times 2q plus 1 minus 5. So we have to kind of unwind that and try to make it look like 2 times an integer plus 1. But we can do. It will work out. Let's just see what happens. So we have to be able to square 2q plus 1. So that's 4q squared plus 4q plus 1. If you need to go over to the side and do a little algebra and multiply 2q plus 1 times 2q plus 1, you can do. and you should get this. Now we're going to distribute the 3 across 2q plus 1. What does that give us?
6. 6q plus 1.
But the 3 gets
mi-
multiplied times the plus 1. So
minus 5.
it's a plus 3, right? Because
Oh,
3 gets multiplied by everything. And so
okay.
put
So
right
that'll be 6q plus 3
minus 5.
minus 5.
All right, let's gather these things together. We got 4q squared. That's all the q squareds we have because we only have q squareds here. But now we have plus 4q plus 6q. What's that all together? What's
Plus 4q plus 6q, that's 10q.
good? And now we have 1 plus 3 minus 5. What is that? Well, we're going to want a plus 1. We can just leave the plus 1.
Wouldn't that be like negative?
Uh-huh. Negative what?
Negative 1?
Exactly. But the definition, good. But we got a little more work to do because the definition of odd doesn't say 2 times an integer minus 1. It says 2 times an integer plus 1. So we need to work on this minus 1 and rewrite it using the QR theorem. This is plus 2 times something plus 1. So what is our integer there? We want to get minus 1. You can put it over here and solve it over here. We want minus
So
1 to equal 2 times something plus 1. What is that something going to be?
just 2 by itself.
You mean
Because
2 times 1? No, because 2 times 1 plus 1 would be 3. We got to go backwards.
it has to be equal to that negative 1, right?
Right.
So the negative 2,
Let's check it. What's 2 times negative 2? If we put a negative 2 in here, what would that be altogether?
that'll be negative 4
Good. And
plus
negative
1.
4 plus 1 would be negative 3. So that's not negative 1. How about negative 1 here?
2 times negative 1 plus 1. Okay.
That'll work, right?
Yeah.
And now we can factor the 2 out from this and this and this, leaving 2q squared plus 5q minus 1. And then we have the plus 1 hanging off the end. And lo and behold, this will be our m. So n squared plus 3n minus 5 does look like 2 times an integer plus 1. We have to talk about why that's an integer. It's the same thing we said before. Since q is in z, we can say it the other way. And sums, products, and differences of integers are integers. Right? There's 2 different ways to talk about why these expressions are integers, but they all involve, multiplication, addition, subtraction. You can call it sums, products, and differences of integers are integers. Our m, which is equal to 2q squared plus 5q minus 1, is an integer. So that's the second part of the definition of odd done. So we showed n squared plus 3n minus 5 equals 2m plus 1, where m is in z, which makes it odd.
Excuse me, Professor, could I ask a question
I
real
wish you
quick?
would, sure.
So when in the other method that you showed where you pull the positive 1 out after the factoring, after squaring the first binomial and then distributing the 3, you pull one of the minus 1 terms out, and then you factor the rest of the values.
Yeah,
And then
yeah, yeah, right, right.
we didn't write it out here, but that's an option. So, for example, that positive 1 after 4q can be brought to the end, and then 4q plus 10q minus 2 can be divided by, can have 2 factored out, and that will give us the same result.
That's right. We could have written
Okay.
this equal 4q squared plus 10q uh, minus plus 1. I guess it's minus 2. Is that right?
Yeah. And no, 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 minus 1. I'm
Oh,
sorry, because we
minus
factor.
1.
No, no, we haven't factored it yet. So
That's right, because 3 minus 5 is minus 2. And then the plus 1, you could just put right there. That's right. You could do it that way.
okay.
And that way it might be easier.
And then those first 3 terms are in the parentheses. You factor them, and then they become the variable, and then you get 2m plus 1.
Right. That's
Okay.
right. There's more than one way to do that algebra for sure. All right. So we're making good progress here. We're working through our universal examples, trying to. Um, our next example was a real nice little example about rational numbers. It goes like this. It's universal. Again, if x and y are rational, then x squared plus y is rational. That was the statement number 5. Just made up a bunch of statements at the beginning of the office hours, right? And, we can work through this one. Do you want to work through this one, folks? Definition of rational in play. It's just a little direct proof. Do you know the definition of rational? We would assume x and y are rational. Always is for direct proof, you just assume the hypothesis, and then our wish is to show that the conclusion follows. The hypothesis is that x and y are rational. That's our P, right? And then our Q is that x squared plus y is rational. So assume x and y are rational. And we wish to show x squared plus y is rational. So we do need to know the definition of rational. Darius, do you know the definition of rational?
The rational, I got n over a, I mean n cross a over b, where a, b, c, I mean a and b are integer of z, and b is not equal to 0.
Perfect. So by definition of rational, so x is rational, so x equals a over b, good, where a and b are integers, they're in z, and b is not equal to 0. And of course, we have also that y is rational, so we need to cook up some letters for them. So like c over d would work, right? Where c and d are integers and d is not 0. And so that's great. So we have all our equations from the definition of rational. Let's look at our wish. What do we really wish to show? We wish to show that x squared plus y looks rational. We could say it looks like e over f, where e and f are integers, and f is not equal to 0, right? So we're trying to prove x squared plus y is rational. Can you do this one? Are you comfortable with this one, or shall we do it? Do you know how to
I
do?
don't know. I could try this one.
Okay, so we'll leave, you finish. Because we've got plenty of examples in the class notes where we did this sort of proof. I'm going to skip 6. Because we've done a lot like number 6. So let's look at number 7. This uses the definition of divides. If A divides B and B divides C, then A cubed divides BC squared. Let's look at that one. That's also direct proof. So we would assume the hypothesis and prove the conclusion, right? So we'll just assume that A divides B and B divides C, and we wish to show that we can factor A cubed out of BC squared. That's what it means to say A cubed divides BC squared. All right, do you know the equations we get from knowing that A divides B and B divides C? By definition of divisibility, I guess that's what they say in WebAssign, but I'm just going to say by definition of divides. What does it mean to say A divides B? Shall we write our definition up here at the top so we can reference it? X divides Y means what? Let's write our definition of divides up here. What's the equation we get if we know X divides Y? You can read it, X divides into Y. Okay, so this is one that is a little tricky for students, but you just think about it, like 3 divides into 12, or 6 divides into 36, or something like that. It means this is the number that cannot be smaller. Okay, X can be the smaller number. They might be equal. What's our definition? Nura, I know you know this one. Y equals X times,
Yeah. Y equals X times K for some integer K.
yep. So we were going to get equations that look like this because A divides B and B divides C, right? So A divides B means B is equal to A times K for some integer K. And then B divides into C means C equals B times, say, N for some integer N. And I want to unpack our wish just a little bit further because the divides definition's a little tricky. So here our X is A cubed and our Y is BC squared. So let's think about the kind of equation we need to get right before we can say that that means A cubed divides BC squared. Darius, do you see what's going on with this definition?
Yes.
So if we're trying to prove that A cubed divides into BC squared, what is the equation we would need to prove happens?
That'll be the Y still stands, right? Y equals
Yeah, the Y here is the BC squared. See here, this is the Y. This whole expression is our Y. Do you see that?
yeah.
And the X is A cubed, okay? So the Y is on the right. So in the equation, we say BC squared equals what?
Equals A Q.
Good. And let's pick another letter since we already used K. Let's say M, okay? Where M is an integer. Good. That's exactly right. So, and the beauty of doing this is it tells us, hey, we got to look at BC squared. Okay, we're trying to prove that A cubed divides BC squared. Okay. So we look at BC squared. Well, that's fine. B is AK, right? So we can use that. And C is BN, but it's getting squared. But when you really look at this, you can see that we don't have A cubed yet. But we need 3 copies of A. We only have 1. But there's a trick here. B is A times K, so we can plug in that again for B. So it's sort of like a little slick trick there. And now we get A, K, A squared, K squared, N squared. And we have enough copies of A now. We've got 1 here, we've got 2 here, so we can pull them out front. We've got 3 copies of A now. And then these other factors are going to be our M. This is our M. And we can talk about why that's an integer. We still have to verify it's an integer. Well, K is an integer and N is an integer. See, we haven't used that information yet, but we can use it now. Since K and N are integers, M equals K cubed N squared is an integer. What operations are being used to build K cubed times N squared? Nora?
Multiplication.
Yeah, okay, great. You got it, Darius. And so we say because Z is closed under multiplication. It's the only operation in play there. So in fact, BC squared, which is what we wanted to say something smart about, equals A cubed M, where M is in Z, which means A cubed divides BC squared. Now those are our direct proofs. We have 3 more in our list here of proofs. Look at number 8. Number 8 is our proof by contradiction. It's if X is rational and Y is irrational, then 2X minus 3Y is irrational. This is an if P then Q statement, right? Here's our P, and here's our Q. But in proof by contradiction, that's going to be our strategy. We could use proof by contradiction. The point is, we need to use an indirect proof. And proof by contrapositive is difficult. Proof by contradiction is going to be the way to go.
I had a quick question.
Yeah.
Uh, if you choose proof by counterpositive or proof by contradiction, does it matter if you use the wrong one?
Well, this is going to be, let's just think about what would happen if we tried to prove this with contrapositive, okay? The contrapositive would be that if 2x minus 3y is rational, then x is irrational or y is rational.
Oh, I see.
That's going to be a real mess, right? But if we,
Right?
right, but the negation is a little easier because we get a little more to work with. We're going to assume, P and not Q, right? So assume X is rational. That's going to give us an equation. And Y is irrational. We'll hold that thought. Not anything. And, right, and 2x minus 3y is rational. That's going to give us an equation. And again, I have a video, the special topics playlist. It's actually a two-part. It's two videos. It's a proof. It's very similar to this. And the point is, now we're going to get an equation from x being rational. We're going to get an equation from 2x minus 3y being rational. And then this piece right here doesn't give us an equation, but it gives us something that we can contradict. So I will say view the video, view the playlist, and then you should be able, and also, we've got something very much like this in the class notes, but at least we can start the proof. It is a proof by contradiction. We do assume the negation, assume the negation. And then what we wish to do is get a contradiction. And what we're going to contradict is that y is irrational. We're going to be able to prove that if we have x is rational and 2x minus y is rational, those together will force y to be rational. And that will contradict our hypothesis that it's irrational. So if we just at least start it, assume x is rational, y is irrational, and 2x minus 3y is rational. So we have some things that are rational, and we have something that's not rational. But we wish to show a contradiction, and it's always going to be you'll contradict whatever is irrational. We wish to show y is rational, which will contradict our hypothesis that it is irrational. That's all we can do with that information. We don't get any equations from y being irrational. About all we can do with that hypothesis is contradict it. Again, there are some proofs where you use the infinite decimal expansion of y in a direct proof involving the definition of irrational, but that's kind of beyond what we know how to do. But we get equations from the definition of rational. We get two. That's kind of the beauty of it. X is rational, right? So X equals A over B, where A and B are integers, and B is not zero. And what's the other equation that we get, Darius, from our hypothesis? We get an equation from X being rational. We wrote that. We should get something from 2x minus 3y being rational. Can you tell me an equation we could write for that?
Sorry, I've been muted.
It's okay. So what would I put on this side? If we know that 2x minus 3y is rational, what would we put here?
Will not be the A, B.
We're going to use x equals a over b because x is rational. But
They are the X.
yeah, the
S equal 2Y.
2x minus 3y. It looks like that because it's rational. And then we just see what I mean? We get two equations. We get one for x because it's rational. And we get one for 2x minus 3y because it's also rational. And now we can work with this. And we can show that y actually has to be rational in this case. And that will contradict our hypothesis that y is irrational. Just set 2x equals minus 3y equals to itself. That's kind of the trick here. And because we have this equation for x, right, we can put that in here. But we also have an equation for 2x minus 3y. We can put that in here. And we can make these substitutions and then look at what y has to be. I said I wasn't going to work this, but I guess I am. I'm going to walk through it with you. So 2 times a over b minus 3y equals c over d, right? Yeah, I'm making those substitutions for the x and for the 2x minus 3y. And then we can just solve for y, right? Let's see, we can say this is 2a over b minus c over d equals 3y, bringing this over as a minus and this over as a plus. And then we can get a common denominator, 2ad minus bc over bd equals 3y. And then we can finally solve for y and just multiply both sides by 1/3. And we get 2ad minus bc over 3bd equals y. So y looks like a quotient. And then we can talk about why the numerator is an integer. Go ahead. So we could just use all of this information about a, b, and c, and d being integers. And b is not 0, and d is not 0. So m equals 2ad minus bc. This numerator is an integer. And n equals 3bd is an integer. They're both integers. And 3bd is not equal to 0 by the ZPP. These are integers by closure properties, by closure of Z. I'm not going to write it all out, but that's the bottom line. So Y looks like a rational number. It's M over N, where M and N are integers, and N is not 0. But you see, our hypothesis was that Y is irrational. But now we've proven that Y is rational. And we can't have it both ways. This makes Y rational, contradicting our hypothesis that it is irrational. And that is the proof by contradiction. Again, I encourage you to watch that video, that 2-part video. Number 9 is really easy. Number 9 is for all x and z, if x cubed is odd, then x is odd. This is another one where you want to use an indirect proof. So what about proof by contrapositive? So our strategy is definitely indirect proof, but this one isn't about rationals and irrationals. We can actually either use contrapositive or contradiction. Either one will work. Like a really nice question might be for me to ask you to just write the correct hypothesis and the correct wish for each of these two proof methods applied to this particular statement, right? So for proof by contrapositive, what would you assume? And what would you wish? And if we did a proof by contradiction, we could ask ourselves the same question, because that's another approach, is proof by contradiction. What would we assume? And what would we wish?
Professor, a quick question.
Please,
Um, I I believe the assumption for both contrapositive and contradiction would be the same. For contradiction, oh, I'm sorry.
really?
Well, for contrapositive, it would be assume x is even and x cubed is, well, that not, well, the contrapositive would be if x is even, then x cubed is even.
Uh-huh.
The contradiction would, oh, I'm
Uh-huh.
sorry.
No, you go ahead. You're on the right track. So let's just write the contrapositive. The contrapositive, you tell me again, the contrapositive would be for all x and z if,
If x is even,
uh-huh,
then x cubed is even.
that's right. But we don't assume the whole statement for a proof by contrapositive. We would just assume the hypothesis.
But wouldn't that be the same for, oh no, because it for proof by contradiction, it would still be if x cubed is odd. Well, not if, it would be x cubed is odd and x is even. Oh, I see.
But the algebra turns out to be the same. Proof by contradiction, we assume the negation and we wish a contradiction, right? We always want, oh, the glare is horrible, but we wish to get a contradiction, right? So here we would assume that there exists an X in Z, right? Such that, what is the negation? There exists an X in Z such that,
X cubed is odd and x is even.
yes. And the fact that X is even is going to allow you to contradict this. You'll use this and contradict that. We wish to show X is even forces X cubed to be even, which will contradict X cubed is odd. It's the same algebra for both. I actually prefer proof by contrapositive. You know, the contradiction we get is we contradict, the fact that X cubed is understood to be odd, but we use this, that X is even. Whereas here we just use the fact that X is even and straightforwardly show X cubed is even. So contrapositive is actually probably preferable.
Uh-huh.
If you can, write a proof by contrapositive, it's generally, it's the more direct of the two indirect proof methods. Because it doesn't confuse you. Like when we have that x cubed is odd and x is even, that can confuse you. You can wonder, well, okay, I've got all this. What do I actually start working with, Do I write an equation for x cubed being odd, or do I write the equation for x being even? See what I mean? And then,
I see.
right, and it can be kind of confusing. Whereas if we just do the proof by contrapositive and assume not Q, that's all we've got. X is even, that's it. So there's no confusion about what we're going to do. We're going to deal with that and then show x cubed is even.
And for the proof by contradiction, we would try to show that x cubed is even.
Yeah,
No.
yes,
Yeah.
it'll force this hypothesis that x is even. We'll use that and it will force x cubed to be even, and that'll contradict the fact that we've assumed it's odd. But it seems silly to go through that when you can just directly prove. You know what I mean? Like it makes it look silly to do it that way, but it is
Uh-huh.
doable. Definitely doable, but yeah. And our last example here, number 10, when it's a does not divides. Again, I'll like I only use proof by contradiction if I have one rational and one irrational, because that's when you really kind of need proof by contradiction. These other ones can be proven by contrapositive. This one says if a squared does not divide b squared plus c squared, then a does not divide b or a does not divide c. So our strategy is to use a proof by contradiction. I mean, we can put that here too for this other one, but kind of the better strategy. The one that we just did, prefer this. If you can use proof by contrapositive, it's preferable. So again, we know we can't prove it directly because it says does not divide, but it's going to be preferable to use proof by contrapositive because it's just easier. But you could use proof by contradiction. But you're just going to wind up contradicting P, right? It's an if P then Q.
If we use the contrapositive, then we remove those do not negate.
Yeah, exactly. Do not divide. Yeah, let's write the
No matter what.
contrapositive. Yeah, help me write the contrapositive of that. Let's do that now.
For all integers a, b, and c, I'm sorry.
You're good. You're good. Keep going.
If a divides b and a divides c,
Yeah, and it flips that or to an and, so we have a whole lot to work with.
then a squared divides b squared plus c squared.
Yeah, and that's just nice and clean. It's just really nice to go from, oh, okay, now we're going to assume that A divides B and A divides C. And then this is what we wish to show, our conclusion. It's just really easy. And this is a nice, this is even a little easier than the other divides proof that we worked with. You know, I mean, the new twist is that it's a proof by contrapositive, but it's actually a fairly easy proof. We would just assume A divides B and A divides C. What do we wish?
We wish to show a squared divides b squared, or b squared plus c squared equals a squared times m.
Yep, we can write both of those. Yep.
You wrote that for an earlier example. I thought it was very helpful.
It's extremely helpful to really translate divides into equations because the divides definition is a little bit convoluted. And it's because we read left to right, and the notation suggests if we just look at a squared divides b squared plus c squared, it kind of, we just read left to right, you know, and we read a squared first. And it kind of seems like we're supposed to be looking at a squared. But when you really
Mm-hmm.
look at what it means for a squared to divide a quantity, it's the quantity that you look at. It's really
Uh-huh.
b squared plus c squared that needs to be observed and examined and substituted into. So do I need to why don't you try, you know, try to write this proof, okay? Now, tomorrow night, I'm going to be giving an extended Zoom office hour for my Math 265 linear algebra course. So I won't be available for an extra office hour tomorrow night. But this is, Darius, do you know how to get equations from this hypothesis using the definition of divides? Can you go back and look at our definition of divides and use it? We can put it as a ready reference. X divides Y means Y is equal to X times K, where K is an integer. It's a, you know, all of these definitions have to be understood. We've got 14 pages of notes. This office hour has gone for 2 hours and 15 minutes. But I think that's a world record for me personally. But it was very comprehensive. I mean, there are a couple of things, gosh, I was just trying to think what else would be on the test that maybe we didn't talk about. There were those fun little problems about perfect squares and perfect cubes, right, that were in the in the WebAssign. They look that find the smallest positive integer k.
Quick question.
I think that looks like a good extra credit problem in my mind is one of those. Yeah, go
Were
ahead.
those? I'm
The,
sorry.
the, the test is still tomorrow, right?
Yeah,
Yeah, because I heard you talking about office hours, and that's what I
well,
was
that's for a
wondering.
different class,
Oh, okay.
a class that has a test on Tuesday. Okay, you had a question there, Nora?
Yes. Would you accept a resubmission for the material to number 10? I noticed while I
Yeah,
was following algebra.
yeah, that's fine. I haven't downloaded that yet, even to grade it. So you get up to 3 submissions and other people, that's fine. I'm not gonna have time to grade that tonight.
Okay.
I'll get, you know,
And I
I'm getting
had
as much done as I can get done. There's sort of an upper bound to what I can do. People are turning that stuff in kind of late.
uh um um I don't it's abbreviated SFF and we talked about it in class. It's factoring smallest
The
I
large
don't know.
standard factored form.
Okay. All right. I will review that. Of course, I need to. Will that be on our? I don't know when we're having
Well,
our
there
test. I
were
think.
there were WebAssign problems, weren't there?
Yes, and I worked them, but I did them early, and I have to go back over them. So
Well,
I will do that.
right. Okay, so here's just an example. Find, I think I did a do later. Find the standard factored form of, n equals say 1200. That would be one to do.
We
And
did this with the factoring tree, I believe,
yeah,
or in WebAssign.
a factoring tree can be really helpful. The way I
Okay.
do it is I just start pulling out primes, I start with two.
Oh,
I can't pull out any more twos, pull out threes, but that's sort of the same idea. Um,
I remember that from class. Okay.
and oh, hang on, I've got a calculator here, and I can just because I can't multiply huge numbers in my head. I could though do um, this one 5, 8, 8, and then yeah, do later standard factored form. Yep. Okay. Yep. We definitely went over standard factored form in our class notes. And I gave you a really big do later in the class notes. It was like a huge number, but it seemed like a kind of good one. And I guess I could just give one more. Find the smallest positive integer. I think I gave you some of these in office hours. K,
Yes.
that makes n equal. Remember we played this game?
Yeah. Oh, yes. Oh, I remember this. Yeah. I'll go back over these. A perfect square.
And the other one would be to make it a perfect cube.
Perfect cube. I'm trying to remember how we did that. We focused on the exponents and
Right.
let's see. So I'm just looking at this. We would
I
want
need a K
something like
here. I'm gonna
perfect
change,
square. I'm
I'm gonna
looking.
change these a little bit for perfect cube. Oh, perfect cube. I meant to say perfect cube. I'm getting tired. I'm gonna make this one 2 to the fourth times 3 and 7 to the ninth times 11 squared. I'll make that for the ninth. I'll put that 7 times 11 squared times k, a perfect cube. Okay, yeah. Yeah, remember, in a perfect square, all of the exponents have a factor of 2. Each exponent in the standard factored form of a perfect square, each exponent is divisible by 2.
For a perfect cube, each exponent would be divisible by 3.
Exactly.
Okay.
And if it was a perfect quartic, like if it
I
looked
think
like
that's 5.
that'd be a quintic. But
Oh,
yeah,
oh.
yeah. Here n would equal x squared. Here n would equal x cubed. A perfect quartic n would equal x to the fourth, and a perfect quintic n would equal x to the fifth. So you could play the game, each x for a perfect whatever. I don't have words for anything but beyond a perfect quintic. But a perfect quartic and perfect quintic. Anyway,
And we would come out with well, K would equal a series of numbers that are raised to powers that equal exponents divisible by 2 for the first and then divisible by 3 for the second.
that's right.
Because
K corrects these exponents. We throw factors into K, but we want to find the smallest K that works. So we don't want to just throw in a whole bunch of stuff. Like to make this a perfect square, 2 to the 5th won't work because 5 isn't divisible by 2. So how many copies of 2 would we need to include with K?
only one.
Yeah, if we put a 2 in K, it'll make this 2 to the 6th. What about for the 3?
We would need we would add one more copy of 3, so 3 squared.
Yeah, we would need one, throw in a copy of 3 to K. So we have a 2 in K and we have a 3 in K. How about for the 5? Would we need to put any?
One more copy.
How about 7s?
We don't need any more.
That's right. So K could just be 2 times 3 times 5, and that would work. And here, to
Uh-huh.
make it a perfect cube, I think you'd need to do something to correct the 4, because that's
Yeah,
not
2
divisible.
copies.
Yeah, you need 2 copies of 2 in K.
2 copies of 3.
Good.
5 is fine.
5 is good because 3 is already divisible by 3.
Do you need two copies of 7
Uh-huh,
and 1 copy of 11?
exactly. You got it.
Okay.
Mm.
Alrighty. This was wonderful, Professor. It was a really great review for me, and I very much appreciate it.
You're very welcome. Thank you so much for coming. It's going to take a while for this to process, so I better,
Quick question.
yeah,
Is this gonna be posted tonight?
I'm going to work on that right now.
Okay, because I'm gonna stay. My next class is at 8 a.m. So, but I'm gonna stay up all night for this. So,
It's never a good idea to pull an all-nighter before a test. It's always a good idea to at least get 5.5 hours, 4.5 hours of sleep, okay? 4.5 is minimum. You need 3 sleep cycles to reset your brain. So if you go to bed, at 2:30 or 3, you're okay. I don't recommend staying up all night. It's not a good idea. I'm going to stop recording.